This problem is a little bit tough the first time we're seeing these things. This is really some pretty straightforward things there, but involves a theorems, involves this thing called the second fundamental theorem of calculus and derivative inverse, which we're not like abundantly familiar with right here. So if you haven't watched the video yet over the theorems, rewatch that, try to give a little refresher about what those theorems are supposed to be. But from your blue packet right there, we got your four big ones right here. If they're asking me to show that a y value is equal to something, the intermediate value theorem just simply says if you have like a y value of 2 and you have a y value of 7, that there has to be a y value in between that 2 and that 7 right there. So anytime you're talking about, hey, show it's in between something, that's what we're going to do for the intermediate value theorem. And see how right here it says show that the y value is equal to something. So right away, I'm thinking intermediate value theorem, all right? The other theorems have derivatives involved in them, and we'll talk about that in a second. But all I did was take the 1 to 3, and it's talking about this h, right? And then so I plugged in the 1 to 3 for that x right there. I did h of 1, did my composition stuff, used my chart. I did h of 3. So when I did h of 3 is f of g of 3. So g of 3 from the chart, g of 3 was equal to 4, and then f of 4 was equal to negative 1. Negative 1 minus that 6 was a negative 7. See how I got a y value of negative 7 and a y value of 3? And so the graph says it's differentiable. Now remember, if something's differentiable, it's also automatically continuous. So that's what these theorems talking about. It says, hey, if it's continuous, that's the only stipulation right there. And then this y value is in between the 3 and the negative 5. So the intermediate value theorem guarantees it's got to cross through all the y values in between that negative 7, 3, and then negative 5 is one of them. So you just got to show that you're getting those for the endpoints that's in between there, and then just jot down IVT, and we'll be good there. Now, when I see the derivative is equal to a number, what jumps out at me first is the mean value theorem. If I see the derivative is equal to 0, that's what I'm going to do Rolle's. It shows that the graph levels off. If I see that derivative is equal to a number, I'm thinking mean value theorem. So it says if it's continuous and differentiable, which is what this thing is, it says it's differentiable, which means it's also continuous. And then I'm supposed to show that the derivative is equal to something. The mean value theorem says show that the derivative is equal to the slope. That's just your slope formula right there, like the f of b minus f of a equals b minus a. And so once I saw the derivative is equal to something, I figured it was going to be mean value theorem. So I jotted that down right away because you probably get stuff for that. And then it says in between 1 and 3. So I plugged in the 3 and the 1. We already did the h of 3 and the h of 1 above here. That's where I got those y values from, the negative 7 and the 3 divided by the 3 minus the 1. That gave us negative 5. And see how we proved that the derivative was equal to negative 5? That's what we got, but that's what your mean value theorem is talking about right there. So usually when theorems pop up on there, they are pretty straightforward. We just have to kind of be familiar with those big ones and we'll be okay. Now letters C and D. All right, I like letter C. Letter C is called the fundamental theorem of calculus. I'm sorry, the second fundamental theorem of calculus. And on the second page of your blue packet, it's at the very bottom. We did notes over this, but we didn't test over this, so you're not used to doing that all the time. But it involves when you're doing the derivative of the integral, you're going to get that inside function. So all you're doing is essentially just taking that x and plugging it in right there, and you're going to have that. So if I tell you to do the derivative of that integral, all you're going to do is take that x and plug it in. That's going to be your answer. That's if you just have an x right there. If you got a whole function right there, you still take it and plug it in. So like I got that f of g of x, but then if you got a function there, you're going to times it by the derivative of that function. You're still doing that here, except the derivative of x is just 1, so there's no point to even talking about it there. So it doesn't matter what this number is, but if you do the derivative of the integral, you could just take that and plug that in right there. And I give you cosine of x cubed, but then you just got to remember to times it by the derivative of that function. The derivative of x cubed is at 3x squared. I plan on making another video with a couple of these type of problems worked out on there with the inverse stuff and with the second fundamental theorem of calculus. We'll have another handout with that and we'll talk about that. But you got to remember to times it by the derivative of that extra piece. And that's what we're using. You're only using that whenever you're doing the derivative of an integral. See how they give us w as this integral and it just looks funky, and you're supposed to do the derivative of that. So if you do the derivative of the integral, you take that and you plug that in, you get f of g of x, and then you times it by g prime of x. So we just have to know that property. You're going to see that again in the future. You just got to practice that. And then you're supposed to plug in the 3. Well, then you're just going to do f of g of 3 times g prime of 3. Take the 3 and plug it in for those x's. G of 3 from our chart, G of 3, boom, is equal to 4. And I got to go f of 4. So then f of 4, boom, is equal to a -1. And then G prime of 3, that's from our chart, G prime of 3 is equal to 2. So then you just multiply those numbers together. And then that's a pretty good problem for us, as long as we're studying this blue sheet and we're kind of just looking at some of those examples and we're memorizing those, because it's not like we did that every single day when we did our normal integrals and when we did our derivatives right there. And then letter D is involving the derivative of an inverse. This one is kind of brand new, so we're kind of learning this thing right now. But on your blue packet, it says if f is the original function and g is the inverse, if I want to do the derivative of that inverse function, we just want to kind of memorize this formula. It's going to go 1 over f prime of g of x. And the way I remember this, the original function is always on the outside. That's the one you're doing the derivative of. The inverse function is always on the inside. Think in for inverse, in for inside. That inverse function is always on the inside right there. So that's the formula that we're going to work with on this one. So when it gives me the G inverse, okay, so G is the original function, G inverse is the inverse function. So before I talk about this, the slope formula that we just talked about from that blue sheet, you're going to go 1 over G prime of G inverse of x. That's how you get that slope. So the G is the original function, that's on the outside. The inverse function is on the inside. And then they're saying that x equals 2, right? So you're going to write the equation of a tangent line. We're going to need the point and the slope here. So if you look at the table, remember the inverse is switches your x and y. So on your G function, look what that y is equal to 2. See on the G graph, you got the point 1, 2. Now if the point 1, 2 is on your G function, switch those around. That means on your inverse function, you got the point 2, 1. So there's our point that we're going to use. And just when you use the slope, you got to use that blue packet there. You're going to go 1 over G prime of G inverse of x, plug the 2 in place for x, G inverse of 2, that's when x equals 2 in our inverse function. What's our y value equal to? So that's equal to 1. And then G prime of 1, that's from our chart. G prime of 1 is equal to 5. There's your slope. Then you do the point slope form. And then just want to mention that, hey, Rolle's theorem, we'll be taking the derivative and set that equal to 0. And then we'll, watch the other video where I'm explaining those other theorems right there. And I'll probably make another video where I'm just doing a couple more examples just like that, because it's not something we're used to doing every single time. Honey.